Okay, I want to welcome everyone to the Dart University 101 Motor and Drives Basics. Just a quick disclaimer here. Everything that will be presented is really at a conceptual level. There may be some specific things that are not quite technically accurate, but basically the intent of this overview is really just to give you a concept of the electronics and in some cases the mechanics behind basic motors and controls and how they work together. So let's first we're going to talk about DC motors and controls. One of the things we want to do is establish a baseline understanding of electricity. The three things actually that we concern ourselves with are something called voltage. So voltage really is the potential. A great analogy of this is water in a tank. So you know that when I'm measuring pressure at an opening at the bottom of a tank, the higher the column of water is, the more potential it has. It's the same concept for voltage. When I empty that tank, when that water in this analogy flows, that flow is current. And you'll see with a larger diameter pipe, more flow or amperage will come out compared to a more restricted pipe. Another analogy of this is over here on the right, where you conceptually and logically, if a pipe has a restriction in it, you're going to get less flow through it. So current, when we're talking about electricity, it will flow whenever there's a path for it to flow. In the case of water, that would be like a pipe. In the case of electricity, it's a circuit or a wire, and it will always flow from high to low potential, and that current flow is limited by resistance. So here's another view of the same concept. You can see here's a water pump. The water, when it's coming out of the first coming out of the pump, it has the highest pressure. When it flows through a restriction in the line, that's called resistance. And we have lower pressure on the output of that resistance. Same thing with a power supply. Power flows from positive to negative, or from high to low electric potential. That flow is measured in electricity. It's in amperage, and it's determined by the amount of resistance there is. So there are two types of two ways to describe electricity. Basically, there is direct current, and in that case, it is the voltage always remains constant, given no other resistance or any other influences on it, and it's always positive. The next type of voltage or current is alternating current. This is what comes out of the wall. This is what's used in power transmission lines. But in the case of a DC control, what we're going to concern ourselves with is something called full wave rectified DC. So if you look at these three waveforms, all we're doing to create full wave rectified DC is we're taking the alternating current, the negative going portion of that, and we're flipping it up to the positive side. So even though it's a bumpy representation, it's still always positive, and it's a simulated, if you will, direct current. So we've got some relationships and formulas that go along with everything we've talked about thus far. One of the basics is something called Ohm's law, and that is volts equals current in amps times resistance in ohms. Another formula we use quite often is Watt's law. That's where we describe power in watts is equal to current in amps times volts. A lot of times in motor control, I use Watt's law quite often. A lot of times when I'm dealing with a brushless motor. Brushless motors are relatively small, and a lot of times instead of being rated in horsepower, they're actually rated in watts. And another piece of information typically that's on the motor nameplate is the voltage rating. So if I know the watts and the volts, I can calculate how many amps I would expect that motor to draw at full load. So we have an example. If I have a 200 watt motor and a 24 volt armature, I would take, using the Watt's law formula, I'd take 200 divided by 24, and at full load I would expect something north of 8 amps to be drawn by that motor. Another relationship for electricity when we're dealing with motor control has to do with horsepower. In a perfect motor, 1 horsepower equals 746 watts. So if you know the motor horsepower and you know the armature voltage, again, you can calculate the expected current. So 1 horsepower let's say it's a 90 volt motor, I would take 746 divided by 90 and get 8.3 amps. But that's in a perfect motor. So allowing for some losses and inefficiencies, I would expect somewhere around 9 to 10 amps for a 1 horsepower motor with a 90 volt rating. And that's pretty consistent with what we see actually on the market. So let's talk a little bit now about magnetism. So when you were a kid and you're playing with magnets, you know that when you take a magnet and put the 2 north poles together, they oppose each other. But when you have a north and a south, they actually attract. So this very basic principle of physics, electromagnetism, actually is the key to creating rotation in a motor. So there's 3 ways that a magnetic field exists in a motor. One is we can actually generate it. The second way is that it's induced. Or the third way is it's inherent in the material of construction. The last example basically is a permanent magnet. So here's another principle of electromagnetism that's key. If you pass a current through a conductor, a magnetic field will be generated around that conductor. What you see in the diagram there is something called the right-hand rule. The direction of the current, if you wrap your hand around the conductor, the direction of the current will be in the direction of the thumb. Now, another interesting fact is if a magnetic field already exists and you place a conductor in it, you will induce a current in that conductor. So let's take all of that and apply it to in this case, a DC permanent magnet motor. So what we've got here is probably the most basic example call out a few key things here. We've got we have a motor winding, or this is a conductor. This piece of wire right here in the middle, and we're going to pass a current through it to create a magnetic field using that right-hand rule. So this wire, this conductor, is, in the case of a motor, this is the rotor. This is the part that moves. The stator is the north and south permanent magnet that is always present and doesn't change. But to get continuous rotation in that rotor, we actually have to switch the power going through it. So that's accomplished through something called brushes and a commutator. So if you'll notice, this commutator is actually split. So as this thing rotates, it will accomplish keeping the current flow such that I've always got a north against a north and a south against a south pole inside the motor. And this rotor, the center part, will always turn. In this case, since we've only got one winding in the rotor, it might be a little jerky. The next slide we'll talk about how to overcome that. Now, you don't see them very often, but another type of DC motor is a field or a shunt wound motor. In that case, you would not see a permanent magnet. You actually would have a second winding that would be powered all the time, not using a commutator or anything. We would just run current through it, and it would generate this similar north and south magnetic field in what's called the stator of the motor. So the rotor turns, the stator is stationary. So let's expand on this. To get a more continuous, smooth rotation, we actually put multiple conductors, and then we have multiple bars on our commutator. Still got the same brushes here. So as this thing rotates, the brushes are energizing the armature conductors that are touching the brush, and we've got a constantly we're creating a field in this rotor that's constantly set up to where we've got a north against a north and a south against a south. They oppose each other, and the rotor will move or rotate. So let's talk about, on DC motors, they have some nice characteristics, unique characteristics. They have very high starting torque. So if you look at this speed torque curve here on the left, you'll notice as we approach zero speed, the torque is actually at its highest point. So that's one of the benefits of a DC motor. If we have a very heavy load that we need to get going, a DC motor is a great solution for that. In terms of speed regulation, DC motors are relatively easy to maintain a nice constant speed regulation. They have a relatively wide speed range, and we'll define what those mean here in a minute. The speed in a DC motor is controlled by adjusting voltage. The current that a motor uses is determined by its rating or its size and its design and whatever is connected to that motor. So when we get to controls, we'll see here in a minute, we don't send current, if you will, to the motor. The motor actually draws current through the drive to the supply. Over on the right here, now we have a kind of another permanent magnet performance curve. You'll see that speed torque, that same speed torque, linear speed torque curve. You'll notice the maximum power is actually delivered at the 50% speed point, and its efficiency is somewhere in the low to mid 80s. So that's not too bad. Actually, that might be a little bit high, but DC motors have been used for a long time and continue to be. So since we're adjusting the motor speed by changing voltage, understanding in an application what our supply voltage is going to be is very important. We run into lots of issues where we have mismatched supply voltage, controls, and motors. So again, it's important here to focus a minute on when I'm getting ready to design a motor and control system. I need to pay attention to or understand what my supply voltage is. So the choices basically are, the easiest one is a battery. This comes into play with truck or vehicle installed systems, portable equipment, and also solar powered systems, either directly from the panel or most of the time actually the solar panel will feed a battery, and the battery ends up being like a capacitor to maintain a more constant DC supply. The next option is actually a power supply. This would come into play where we need to, our supply voltage is AC or line voltage, but we're using a low voltage motor. Typically we run into this when we have smaller motors. For example, 24 volt DC motors is a very popular size. So a lot of times folks want to use a 24 volt motor in a system whose supply voltage is actually coming from the wall, if you will. And then the last option would be actual line voltage. We'll mention overseas, but for our discussion today, we'll focus on 120 volt, 60 cycle. So this is what's important. You need to know this. Think about the supply voltage, the standard input and output voltages for controls, and the motor voltage. You really need to think about all three when you're choosing the components of your system. You don't want to have a 120 volt in, 90 volt out control try to run a 12 volt motor. It's not a good match. So how do we get DC? What's going on in the control to convert AC voltage to DC voltage? Well, it's a real basic circuit called a diode bridge, and this is how it connects. So what happens is half of the bridge will conduct when the AC voltage is positive, and the other half will conduct when the AC voltage is negative. What the result is, if you remember from a previous slide, it's full wave rectified DC. But in this setup right here, we're conducting all the time. We're not, remember, we need to control the voltage to the motor, to the DC motor to get adjustable speed. So what we need to do is actually turn these diodes on and off. A device that will do that is something called a silicon controlled rectifier, or SCR. So basically, an SCR is a diode with an extra input, something called a gate. The gate is where we, like it sounds, is the method to turn the diode on and off. So if we replace these diodes in this circuit with an SCR, we're going to end up with something that we can adjust voltage with. So let's go back to our full wave rectified DC diagram again. Here's some things to know. When we rectify AC, the 120 volt line voltage, the peaks can be as high as 160 volts. If it's 240 volt, they can be as high as 320. But the average, this line right here, is either 90 or 180. So that's why we have 90 and 180 volt SCR rated motors. The 90 and 180 didn't come from anywhere. It wasn't made up. It is allowing for the fact that an SCR drive control is more than likely being used, and it's going to generate, when you take into account or you tolerate fluctuations in the AC voltage coming in, we know we can generate at least 90 volts out on average with 120 in, or 180 out with 240 volt in. So the way that we adjust the voltage is now by gating that SCR we just talked about. So what you do is the cycle actually begins at 0 and goes up to the peak, but the way that an SCR works, it cannot turn on at the 0 point. You have to get partially into the cycle before you can turn on the SCR, or else you'll damage the SCR. So that characteristic of the SCR is somewhat limiting. So they have to be turned on after what's called the zero crossing point, and they can only be turned on and off once during a voltage cycle. So that means the switching frequency is going to be limited to about 120 cycles a minute for 60 hertz power, and it's 100 times for 50 cycle power. What's the big deal about that? Well, it actually can produce some hum from the motor. Depending on the application, that may not be desirable. So, still building on our SCR drive design. We now have a gate in our SCR, and we need some logic that's going to control when to turn these things on and off. So when you see a control and it has something called a speed pot, what you're doing is that speed pot is talking to this logic to tell it when to turn off and on. The other things that can influence that are the minimum and maximum setting, the accel and decel, IR comp, and current limit, and we'll explain those here in just a minute. So all of the speed pot is talking to this logic, and all of these settings within that logic are telling these SCRs when to turn on and for how long. And the result is an adjustable voltage out to this load, which in our case is a motor. So here's another drawing, basically the same thing. Let's take a look at this a little carefully here. So I've got my AC supply coming in. This happens to be, it's single phase. I have my speed pot, and I've got my motor. This is the most basic DC connection, if you will, that we have. So let's look at the speed pot here just a minute. What's actually on these three connections, what's happening is there's actually voltage coming out of the control to the speed pot. So the speed pot, when it sits on the bench, it's not connected to anything. Obviously, it has no power on it. So we have to supply power to it to make it work. So the speed pot high lead is where that power comes from. you'll notice I've got a switch in here. One of the ways to shut off the motor is to open up the speed pot high lead. We call that an inhibit circuit. Basically, I still have AC power connected. Everything's live and ready to go, but I've opened up the speed pot lead, and what happens is the power goes away from the speed pot, and the input signal effectively goes to zero. Because the way that this works, depending on where I've got my speed pot set, as I rotate it, it's going to change the voltage potential. Remember, we talked about that between the wiper and the low lead. So one input to our logic is the speed pot, and we measure the voltage between wiper and low. Typically, this is somewhere between 0 and 12 volt DC. It's a logic level signal, if you will. Obviously, another way to shut off a control is to open up or disconnect the AC power. And then over on this side, there's a couple things going on here. We're sending voltage to the motor and to create rotation in the motor. Basically setting up the opposing magnetic fields inside that we talked about. The rotor will turn and we get rotate, we get work out of the motor. When the motor is turning, it actually is a generator as well. So there's something called EMF, or you may hear electromotive force. You may hear it called back EMF. This is actually voltage being pumped back into the control. Sometimes this can be damaging, but in the normal case, we actually use this to get an indication of whether the motor is speeding up or slowing down for whatever reason as part of the IR comp circuit. And again, I will explain that a little bit more in a minute. But we're actually watching this voltage. We're comparing. We're looking at this wiper low voltage right here. If my speed setting or my speed command remains constant, I want the EMF to be constant as well. That tells me my motor is running at a constant speed. If the motor speeds up for some reason, the EMF will increase, and the IR comp circuit will tell the logic, hey, I need to send less voltage to the motor to maintain constant speed. And conversely, if the EMF goes down, the logic knows through the IR comp circuit to increase the voltage and speed that motor up. So there's a lot going on inside. This triangle here represents the logic. So I've got my speed pot wiper voltage is one input. The motor EMF we just talked about is another input. My minimum setting, which we'll explain in a minute, maximum IR comp, whether I've been inhibited, and then even the current limit setting. All of that is being used in the logic, in the control, to turn on and off, the timing of and the length of how long we gate the SCR and tell it to turn on. So let's go through these here a minute. These are the typical adjustments on a variable speed control. The main speed pot, that's the signal input. That's telling the drive how fast we want the motor to go. Minimum speed, it's an offset to zero. So even though we may turn the main speed pot all the way down, we can turn up the minimum adjustment. We may, for application reasons, may never want the output voltage from the control to actually go to zero. Similarly, but on the top end, we have max speed adjustment. There may be a reason why we don't want the control to actually output the maximum voltage it's able to. So it's kind of like a not to exceed setting. There could be equipment or application reasons why we don't want to go any faster. Again, IR comp we talked about a little bit. This is basically where this is an adjustment to how aggressively we want the control to react when it sees a difference in the input or the speed setting coming in, whether it's a speed pot or some other means, and the back EMF from the motor. Current limiting is it's a safety adjustment for the control and the motor. Again, we're not supplying current per se. We're not adjusting the current, but we can limit the current. So you'll see typically we will set this somewhere from 125 to 150% of the motor's full load amp rating. Current limit is a circuit. It's not a fuse. It's intended to protect against long-term motor overloads, either caused by a problem in the motor or something going on to what's connected to the motor. Now, the way that the circuit works, it does not kick in right away. If you remember back to our speed torque curve for a DC motor, it's going to generate maximum torque. Therefore, it's going to pull maximum amps when it's starting from zero speed. We need to allow the motor to get up to speed when it's first starting. So we don't want the current limit circuit to kick in right away. There's actually a few seconds delay. Acceleration is an adjustment that it's also called a soft start. We may turn a control on, or we may we want to run the motor faster by adjusting the speed pot rather than respond to that input change immediately. The accel will actually allow us to ramp up softly, from zero or from the previous setting up, and this is desirable in some applications. If you think about some bottles on a conveyor, if you want to speed that conveyor up, you don't want it to jump up in speed, otherwise we'll knock all the bottles over. Conversely, if we're slowing down a motor, deceleration does the opposite. And when we're turning it down or turning it off, the voltage, rather than shutting off immediately, actually will have more of a decay. So here's another illustration of this. Typically, a speed pot has about 270 degrees rotation, unless it's a multi-turn pot. But usually most pots have got about 270 degrees of rotation. The minimum setting, the minimum adjustment we just talked about, usually is somewhere between 0 and about 30% output of the drive. So we could turn the minimum adjustment all the way up, and even though the speed pot's at 0, we could still be putting out as much as about 30% of the control's capability. And then on the other side, the maximum usually has somewhere between 50 and 100% output adjustment. So basically, what these two adjustments are doing is they're setting the range of the main speed pot. Now, there's some gotchas that can get involved with DC motors and controls I want to make you aware of. There's something called form factor. Form factor is a spec. You usually see it on a motor. It is an indication of how the motor is designed and built. So if we go back to our direct current graph, it's a pure straight line. The form factor is a perfect 1.0. When we use full wave rectified DC, remember, it's actually pretty bumpy. It has some relatively high peaks but the motor is going to find the average of that waveform. All those windings inside of that motor act like what in electricity is termed is an inductor. It kind of acts like a filter. So it'll have an averaging characteristic to it, but because this is not pure DC, the form factor is usually on an SCR, what's called an SCR rated motor, is somewhere between 1.3 and 1.4. So here's the gotcha. If you're using a form factor 1, or which you don't see, but like a form factor 1.1 motor on an SCR drive that has an output form factor of 1.4, you could get into trouble if the motor is running, if it's in a continuous application or it's running near full load. Basically, SCR rated or 1.3, 1.4 form factor motors are beefed up in their construction, and they usually have higher levels of insulation so they don't get hot. Okay, here's another potential gotcha. I kind of mentioned it before, but I want to emphasize it. Again, the way that an SCR control works, when we want to slow down the motor, we're reducing the voltage. The way we do that is we keep moving this gating point of the SCR to the right, so we end up with narrower and narrower slivers of voltage. When you want to run, or if someone wants to run a 12 or a 24 volt motor on a 90 volt output control, basically we're hitting that motor with spikes of voltage. The motor will run, it'll operate, but the potential is at least that you're going to potentially generate faster than normal brush wear. If you think about it, that brush sitting on that commutator we saw early on, you're pulsing voltage through that. It can break down the brush material a lot earlier than expected. And then the other thing is that motor may run actually pretty hot because, again, we're not sending a nice or something near a DC voltage to it. We're really just sending voltage pulses or spikes. So the solution for that would be to get the output of the control down nearer the 12 or 24 volt DC on that motor. The way to do that is you can use a step-down transformer. If your supply voltage has to be 120 or 240 volt, use a step-down transformer, drop the AC voltage down to a lower level before it goes into the control. And then what you'll end up with is you'll be able to have, more of this waveform coming through, but the peak is a lot less, and the average is somewhere nearer that 12 to 24 volts you're looking for. Also, another gotcha here is, and we run into this quite frequently, base speed on a 90 or 180 volt DC motor is somewhere 1750 to 1800 RPM. If the customer or the user is trying to run that motor down in the 100, 200 RPM range, again, the way to do that from the control only is you're hitting it with these spikes of voltage. Even though it's a 90 volt motor, 90 volt output, long term it's not a great solution. Not to mention probably your operation, motor might start to cog. You really need to put a gear reducer on that motor. DC motors really operate best in the 20 to 30% and above portion of their speed range. Okay, here's another gotcha. This is where we got to pay attention to what the motor is connected to. In this case, I've got a load. It's in the vertical plane, but I'm winding this up. So in this case, the voltage is coming from the control into the motor. We're getting rotation here, and we're pulling this load up. This is fine. There's no issue here at all. But the opposite of that, if this load is dropping, remember the EMF, back EMF we talked about? If this motor gets going fast enough, it actually can generate a damaging level of voltage back into the control. We have protection against that in the control, but at some point, this voltage could get high enough to where it will overcome that protection. So we're motoring here, but in this case, we're overhauling. And we got to be careful here. When you get into an overhauling situation, you may need a different type of drive, which we'll touch on briefly a little bit later, called a regenerative drive. Okay, the last instance is a high inertia load. And in this case, this load is okay, sort of. If you can envision, I mean, we've got this, basically it's a big gigantic flywheel. There's a lot of inertia involved with this kind of a load. And what we may need to do at the control level is actually turn up that axle adjustment. We may not want to hit the motor. If I want this thing to go half speed even, we may not want to dump that full half voltage on the motor right away. We may want to have that voltage gradually build, because the problem is if we try to accelerate this high inertia load too quickly, that motor is going to pull a lot of amps. It could be 2 or 3 times its full load nameplate rating, and you could damage the control or the motor. Okay, there's one other type of DC control I want to talk about, and that's called a pulse width modulated or a PWM drive. So going back to our previous diagrams, we have direct current, we have full wave rectified DC, which is what we get from an SCR control. We've got these 60 or 320 volt peaks, and it's got a form factor somewhere around 1.4. If we could turn on the SCR, the device that's switching the, if we could turn that on more frequently and more times in a cycle, we actually could start to flatten this waveform out, bring the average up higher, and have something nearer to a perfect 1.0 form factor. That's what a PWM drive does. SCRs are not used in PWM controls, again, because they're limited, that they can only be turned on once during a cycle. PWM drive uses a different device, usually a MOSFET or an IGBT, which are different types of transistors, and we can turn those on and off many, many times per second. So you'll see, especially from, well, you'll see 130 volt armature motors in the market. They really need to be used with a PWM drive unless they also have the motor has an SCR or a 90 volt rating. So what's going on with a PWM drive? Basically, instead of working with AC alternating current, our supply, once it gets to the transistors that's turning it on and off, is actually DC. So if I have a line voltage PWM drive, the front end part of the control is purely power converter, changing AC to pure or very near pure DC. Then what we do is we turn the transistors on and off. So if you allow more of this voltage to come through, you have a higher average. If you turn it on for a short period of time and leave it off for more, the average time drops, the average voltage drops down to something lower. So that's how you adjust the voltage out. It's by the amount of time the transistors are on. We're modulating the width of the pulse. So that's where pulse width modulation comes from. The other thing to notice is the peak voltage. The peak voltage is actually lower. So even if I have 120 volt AC, my peak is not as high because of the power conversion on the front end. So it's a much cleaner, much nearer to the form factor is much nearer to this magic 1.0. Okay. Still with me, everybody? Oh, yeah, you can't talk. There's two specifications I want to cover in a control that can be confusing. The first one is speed range. So speed range is defined as the lowest to highest speed of the motor at which the control is able to maintain the stated speed regulation. So that's kind of a mouthful there, but let me bring in the second one. So speed regulation is the amount of speed, actual speed variance is expected above or below the required speed. It's usually expressed in a percent of motor base speed. So let's throw some numbers at this. 1800 RPM base speed motor, the control has a 1% speed regulation spec. So that means 1% of 1800, that means anywhere in the speed range of that motor, 0 to 1800, that I could be plus or minus 18 RPM and still be in spec. At the higher speeds, that's quite acceptable. But at lower speeds, if I was trying to run that motor at 100 RPM, this is kind of where we get into trouble, and why I said before, you don't really want to run an 1800 RPM motor down toward 10% of its output, because the control and the motor can both be in spec and still have your actual RPM be anywhere from 82 to 118. So again, the speed range is the actual speed of the motor where the control is able to maintain that speed within whatever its stated spec is, typically 1%. Okay, so let's have a really quick review. What are three things that must be considered for any adjustable speed motor application? I'll answer that. The first one is the supply voltage available. Again, remember, it could be DC from a battery, DC from a power supply, or AC from a wall outlet. The other thing to consider is the armature voltage. We want to match, we need to understand what kind of voltage output standard motor controls offer based on their supply voltage. So a 120 volt SCR drive, standard output is 0 to 90 volts. If you have a 90 volt armature SCR rated motor, that's a good match. If you have a 12 or 24 volt motor, it probably is not. So the standard input and output voltage of compatible speed controls, you really got to look at all three of these things at the same time. Okay, let's switch over to AC motors and controls. So, one of the most common electrical motors is called an induction motor. It's also called asynchronous because an induction motor always runs at a speed less than what's called synchronous speed. We'll try to define this along as we go. So what is synchronous speed? It's the speed of rotation of the magnetic field in the motor, and it depends on the frequency of the voltage being applied and the number of poles in the motor design. So an induction motor always runs at something less than synchronous speed because the rotating magnetic field in the stator this time is always leading or moving faster than the induced flux in the rotor. I'm sorry about all the definition there, but we'll show you some diagrams that'll clear that up, I think. So there are two basic types of induction motors. There's single phase and three phase. Single phase motors are described as not self-starting. So they need something else to get moving initially, and that typically is a capacitor. All right, so let's get into this here a little bit. We're going to build on our electromagnetic principles we talked about in the right-hand rule, so keep those in mind. So what we have here is an induction motor. You'll notice it has three phases, A, B, and C, and the windings, in this case, rather than being on the rotor, the windings are actually in the stator. The rotor in the middle is what turns. What is going on in this rotor is there's actually conductors in this rotor. If you remember, when a conductor is introduced into a magnetic field, it will create a current in that conductor. But oh, wait a minute. If there's a current in the conductor, it will generate a magnetic field as well. So if you remember back when we started, there are three ways to get a magnetic field in a motor. You generate it, you induce it, or it's inherent in the material like a permanent magnet. In this case, in the stator windings, we are generating a magnetic field, and in the rotor, because it has conductors in it, we're inducing an opposing magnetic field. So that is the concept, that's the electromagnetic concept of what's going on inside of an induction motor. So this field, because we're using a control, we'll see here in a minute, to energize these stator windings in a sequence, the field is moving around. While that field is energizing, the conductors in the rotor are seeing current induced in them, and they are creating an opposing field, but it's always lags behind the stator flux or magnetic field. So that lagging is referred to as slip. So we refer to this as an asynchronous motor. That's the technical term for it. So we talked about it already. Rotor is a cage that accepts conductors. We get this induced magnetic field in the rotor, and we get rotation. The speed of the rotating magnetic field is what is the synchronous speed. So how do we get that? How are we energizing that stator winding? So the most common three-phase motors, we need to have a three-phase output control to be used. So the big difference between DC and AC is we're not using voltage to change the motor in an induction motor. We're using frequency. So where does that frequency come from? Well, what's interesting is in a variable speed or variable frequency AC control, we actually take line voltage and convert it to DC. And then we pulse width modulate that DC out to each of three phases. So we're sending this type of voltage, which the curve, this is the effective voltage that the individual stator winding sees, and we can adjust the frequency by adjusting the PWM switching. I hope all that made sense, and you can go back and take a look at it and review it. That's the summary of a lot of information out in the net, but try to boil it down to a simple concept. So AC motors have their own characteristics. They have modest starting torque, not as strong as in a typical DC motor. Big advantage is no brush maintenance. Don't have to worry about brush wear. The speed regulation is good. The range may not be as broad as in a DC application, but it's good. One other aspect is the speed torque curve is nonlinear. Remember, on a DC, it was a straight line. Depending on what type of motor you're using here, and we don't really show an asynchronous, but you get this nonlinear speed torque curve. So depending, if you're running at some particular speed, your sizing of your motor, depending on what type you're using, could be dependent on the operational speed at which you're running. So a little more definition here. This is good to know, but not critical to have to know, but it's good to know. So the role of poles. Motor pole, when you hear somebody talk about the number of poles in a motor, it's related to the number of sets of three-phase windings. So in the simplest motor, there's a single set of three-phase windings. Those windings create a single set of north-south electromagnetic poles. So this motor is said to be a two-pole motor. That's the simplest motor. As the voltage in the phases rises and falls, the strength of each winding rises and falls, and this creates rotation we've talked about. In a 60-cycle system, this results in a base speed of 60 hertz or 3,600 RPM. So that's 60 times 60. That's where a 3,600 RPM base speed induction motor, that's where that number comes from. In a 50 hertz system, the base speed is 300 RPM. It's 50 times 60. So the next most complex, but also the most common induction motor has two sets of three-phase windings. So it's called a four-pole motor. It has a base speed, most typically, of 1,800 RPM. So you can see, if you got a six-pole motor, base speed is typically 1,200 RPM. Eight-pole motors, 900 RPM. You can do the math here and see how that's all working. So Here's a diagram that shows what's going on inside of a variable frequency drive. So in this diagram, we have three-phase AC supply voltage coming in. So here's my three phases coming in. And remember, building on what we've talked about, we rectify it, and then we filter it using an inductor and one or more capacitors. And what we end up with is something called the DC bus. This is the pure DC inside of an AC drive, which is a bit ironic. And then we send it out to the switching transistors to accomplish the pulse width modulation. Woo! We're building on ourselves here, guys. And what we end up with is this adjustable frequency by simulating this sine wave voltage using the PWM output. So in terms of control adjustments in a VFD, you know what? They're basically the same as in a DC drive, except you may run into something else called boost. And boost is it's an adjustment where you can actually more or less overspeed the motor when it's first starting. It provides this extra boost of frequency to get that motor started. Remember, AC motors don't have that same ultra high starting torque, so we may need something from the control to help get that motor going. So single phase AC motors typically are capacitor start, permanent split capacitor, shaded pole, and universal. Elemental, fundamental thing. Cap start motors cannot run at anything other than full speed. The reason is, if you put a variable speed drive, a VFD, a variable voltage supply, whatever it is, you put on cap start motor, the minute you start to slow it down, the capacitor will kick in and bump it right back to full speed. I wish I had a nickel for every phone call we got for someone who has a cap start motor that wants to adjust the speed on it. The only solution is change the motor to a different type. So, what flavors of variable frequency drives can you get? So you can, it's possible to find 115 in, 115 out. These would work. A 115 VAC out variable frequency drive would work well with PSC, shaded pole, universal type motors. By the way, 115 volt, if you're not aware, it's always single phase. Another type would be 230 volt single phase in, 230 volt single phase out. Works well with the same PSC, shaded pole, universal motors. Not real common, but they are out there. And the motors are most definitely out there. Here's a fairly common type. We have 115 volt in, 230 volt, three phase out. This is sometimes called a voltage doubler drive, probably because there's a large installed base. They're relatively inexpensive. There's high volume. For market reasons, there are a lot of 230 volt, three phase AC induction motors out there, but they're used in pieces of equipment that plug into the wall. So your supply voltage is 115 volt. How do I create 115 out of 230? Now you put gigantic capacitors in the drive to really boost the voltage. And then the last type is 230 volt single phase in, 230 volt three phase out. It is possible with single phase motors that we mentioned before, permanent split capacitor, shaded pole, and universal, to adjust the voltage to them to get variable speed. Everything we talked about before was variable frequency. On those single-phase type motors only, it is possible to adjust the speed by adjusting the voltage coming in. So to do that, we use something called a Triac. It's a light dimmer. It's a fan. It's the fan. It's like the fan control, your ceiling fan control. A Triac is a device that's similar to an SCR in that it can only turn on for a portion of the waveform. When doing this, we're adjusting the average voltage. The thing about a Triac is it can operate in both positive and negative voltages. So we just basically take the regular AC and we cut this part out. That effectively drops the average voltage to the motor, and you can slow that single-phase motor down. There's some limitations to this. It's a very basic control. There's not a lot of speed regulation, and speed range are limited, but folks use them all the time, especially in small pump and in exhaust fan basic blower type applications. Okay, so let's talk about brushless DC motors and controls. We're continuing to build on the electricity, the magnetic, the control principles we've already talked about. So this diagram should look very similar to the AC synchronous motor. In fact, it is very similar, except instead of having a squirrel cage rotor with conductors, we actually have a permanent magnet on the rotor. The stator of the motor, where we have the three-phase windings, is basically, effectively, it's identical to an AC motor. So now, because on the rotor, the flux is inherent, it's not generated and it's not induced, this type of motor is actually referred to as a synchronous motor. So that means that there is no, or very little, if any, slip. We're not dealing with slip as a common occurrence in this type of motor. The other effect is we can get very high starting torque, like a DC permanent magnet motor. And we also, because we can run at synchronous speeds, we're really limited on how, in terms of motor RPM, we can go much higher than what you typically see with other types of motors. Okay, so bear with me on this diagram. It's a little bit busy, but it builds on the same concepts. If we have our power coming in, if this is AC, then the voltage has to be converted again to DC, and here's a little filter here, and here's my three-phase output, just like we saw on the VFD earlier. So I have three different outputs. I'm talking to three different phases in the stator. However, to maintain synchronous speed, we need to know where the rotor is relative to the stator. We need to know where the rotor is position-wise relative to the stator so that the control knows which phases to fire when. I'm not going to go into all the detail behind that, but just know that in a brushless DC motor, the most common type have what are called Hall effect position sensors physically embedded in them. This information is fed back to the control. So the control, no, that's one of the inputs to the logic, and the control knows when to turn these transistors on and off. Another aspect of for a brushless control and motor is the control will generate what's called a trapezoidal type output. So the waveform looks more like a trapezoid and not so much as a sine wave. This gets into some of the physics and the design of the motor and the drive that is beyond this discussion. But if you hear trapezoidal output, probably talking about a brushless system. So let's compare a brushless motor characteristic to some we've already seen. One of the things is energy efficiency. The efficiency on brushless DC motors is well into the 90% range. Again, like an AC motor, there's no brush maintenance. We can get higher torque output for a given weight and size of the motor. This can be very important. If you look at this, you'll notice the brushless torque curve is way out here. It's similar in that it's linear to a permanent magnet DC, but we can get a lot more torque in a similar package, and part of it has to do with the fact that we can run these at higher speeds. 50,000 RPM on a brushless DC motor is not unheard of, and there are applications that can benefit from that, if not actually require that. Quiet operation. The switching frequency of the control is above. It's so fast it's above the audible range. So you'll find one of the benefits and one of the reasons for using brushless DC is the fact that the motor and the control operate very, very quietly. For that reason, you'll see them used in medical equipment quite often. And again, we have the really nice high torque at low speeds available to us. One of the things I've touched on a little bit, but this diagram, even though it comes a little bit late, does illustrate between an AC and a DC motor this relative starting torque gap. That the different characteristics between AC and DC, this gap here that may be critical in some applications. Okay, I haven't heard too many beeps on the phone. That means most of you are hanging with me, and I really appreciate it. Let's focus a little bit more on controls in general, and so let's talk about packaging. Typically, for most suppliers, there's really only two choices: a chassis and enclosed. But there are some manufacturers out there that actually make a panel type control package. So the chassis, obviously the electronics are exposed. This is intended to be mounted inside of a control cabinet or a control box with other components. The enclosed model is intended to be installed by itself. Typically, it'll have conduit fittings, so you can keep water and dust and other environmental things out of the control, but run your wiring into it. And then the panel mount basically is just like a meter where you would cut or punch a hole out, and this would slide in, and typically would have a gasket around it. So chassis and panels are 99% of the time are relying on some type of bulkhead or control cabinet or box that the customer would supply. The enclosed model can be installed on its own. When you get into talking about control packaging, whether it's let's focus on enclosed models. There's something called a Nema or an IP rating that will indicate the measure of resilience to things like dust and dirt. direct water, rain if it's outside, or direct water washdown if it's in a clean area, even corrosive materials that are in the atmosphere. So here's a nice little chart that shows how Nema ratings relate to IP ratings, and you'll see these used somewhat interchangeably. Nema ratings probably are still used in North America more. IP ratings in North America and definitely in Europe and Asia. So let's talk more. So we're talking about control options or features. One of the most common is, hey, I've got my motor, I've got a control on it, I'm controlling the speed, but I also need to reverse that motor. Well, in AC and brushless DC motors, because the control is in charge of the timing and the sequence of firing the phase outputs to create this rotating magnetic field, they actually are also can control the direction of the motor. So in an AC synchronous or asynchronous induction, I should say, and brushless DC motors, the reversing is accomplished in the control itself. That actually can be an advantage, especially if there's a lot or some rapid reversing required by the application. For the simpler DC brush or SCR type motors, the way that since we're controlling voltage, what we have to do to reverse the motor is to reverse the polarity of the voltage. So basically, we're just going to take the two plus and minus armature lead, and we're going to reverse or flip them. So that can be done with a switch, or it can be done with a relay. Reversing on a DC brush motor is not required all that often, if it's more of an exception than the rule, and using a switch is perfectly fine. But if it's a automatic, if it's a frequent, and when I say automatic, it's tied to a photo eye or a limit switch or some sort of proximity sensor, you probably want to use a reversing option that employs relays. Some considerations for DC. When you're using a switch, again, there's really no means if the motor's running full speed in one direction and you slam it into reverse, that motor is going to pull a lot of current. There's really no protection available in a simple switch to protect against that. So you need to be careful. The motor really needs to be stopped when you're using a reversing switch before you ask it to go the other direction. When you use an option that employs relays, usually there's some other circuitry along with it. It may or may not employ a dynamic brake resistor. So in this case, if we either tell or a limit switch or a PLC or something is telling that motor to change direction, the first thing that happens is the relays disconnect the control from the motor, and they connect in its place the dynamic brake resistor. And what that does is that dumps all the back EMF energy out of the motor across this resistor. Once the logic sees that the motor has stopped, then it allows the relays to change state and have the motor operate in the other direction. So it's really important when we're reversing, especially a DC brush motor, that we pay attention to under what conditions the motor needs to be reversed and to what extent we need to protect against what's called plug reversing that motor. So let's talk about some other options. It's much more common these days than ever that a motor control is actually being controlled by some other higher intelligence device. could be a human-machine interface, a programmable logic controller, or a microcontroller. All these are generally termed SCADAs. The types of signals normally sent are the speed setting. These SCADA devices will tell the control how fast I want the motor to go, and also will send it start and stop commands. One of the things to consider whenever there's any external control devices being connected to a motor control is something called isolation. We need to be careful that the signal wires coming in are not they're not powered by a system that's referenced to earth ground. If there's any question about that, we need to provide what's called isolation. So you can either use an isolated output from the SCADA if it's available. If it's not, then we may need to put an option card like a 4 to 20 or a 0 to 10 volt DC. Those are typical signals that will provide isolation between the SCADA and the control. Okay, I'm going to wet my whistle here. Let's talk about something referred to as digital control. So going back to our diagram, remember on an SCR control, we've got this logic section. Basically, what we do with a digital control is rather than use discrete chips and resistors and capacitors only, we actually will add a microprocessor. You'll notice physically on the processor itself, all along the edge, there's all kinds of pins there. Many important. Those are all inputs and outputs. That means that we can get into much more sophisticated levels of control. We can do a lot. We can have a lot more things going into the logic, and we can have a lot more information coming out of the logic of the control. So adding a microprocessor to an SCR control will enable us some things here. One, it's better speed regulation. All the logic is executed really inside of what amounts to a computer. It also, did you catch that? It also enables the support for a digital human operator HMI or operator interface. So now instead of just having an on-off switch and a speed pot, we actually have a alphanumeric display. We have push buttons, and we have potentially even some other annunciator type lights that'll tell us what's going on with the control. Again, because we have a processor inside, we actually can offer customer configurable inputs, outputs, and even alarms. Alarms not only for what's going on inside of this control, but also what's going on with the process. The digital control actually will increase the effective speed range of the motor. Because we have finer control and we have automated compensation for changing loads and environmental things, environmental conditions, we can actually more finely control the motor to an extent that we may be able to run it somewhere in 100 to 1 range. We might even be able to open up the range enough to eliminate a gear reducer. We can actually set up master-follower type schemes. So this would be used when there's 2 or more motors and they need to run in some proportion to each other. So the master or the leader and then the follower, typically the follower is running at some percentage of whatever the master is. The traditional way to set this up might be to use something like a PLC, but if that capability is built in the drive, obviously we can save a lot of time and money going that route. I mentioned better speed regulation under ambient conditions. So on a typical SCR drive that we've been talking about, even though there's circuitry and design to be able to work in a fairly broad operating range, there is an issue with something called drift. The chips and the components used to put a basic SCR control together, they do have temperature specs on them, and even though the variations may be small, when you add them together, they can show up on the performance of controlling the motor. Nice thing about a digital control is those can all be compensated for automatically and much more effectively. And then probably the last thing is, because we have a brain, a real brain inside of the control, it sets up things like serial network communications. So now we can share, we actually can have computer inside talk to a supervisory computer at the plant or even within the piece of equipment itself, if it's an OEM. There can be remote monitoring and control, program changes uploaded and downloaded, storing of good and revised programs, and it even sets up things like wireless, Bluetooth, and even Ethernet type conditions. So again, adding a microprocessor to a traditional control opens up many, many more possibilities. So here's, again, to recap where we were, the traditional SCR control. We've got a speed pod input. We're using back EMF from the motor to get an idea of how fast the motor is actually running. A digital control is closed loop. And that means that we need to add some sort of speed sensor, usually called an encoder, mount that to the motor or somewhere in the motor drivetrain. So these pulses that are generated from that encoder are fed back to the digital control, and for information, but also for automatically making motor speed changes under load conditions, environmental conditions, whatever it is that may be causing that motor speed to change. The encoder tells the drive, tells the control exactly how fast that motor is going in a different way, and we have a much larger range of response to the motor. The control will actually go to full output if it needs to get that motor to run the proper speed. In fact, one of the classic troubleshooting points of if the motor's running full speed only is, hey, for some reason I'm not getting any encoder feedback to the control. So again, another way to look at the enhanced capabilities, very tight speed regulation, because we have this very positive, very true encoder feedback. Multifunction operation, meaning that we can have this run in a rate, RPM, feet per minute, gallons per minute, a time mode, minutes and seconds, hours and minutes, or we can again set it up to be a follower in a master follower configuration. Improved operator information. If you think about it, 0 to 10 on a speed pot dial can mean many things. But if I can configure the display to read out in engineering units that the operator can relate to his piece of equipment or the actual part of the plant he's running, that's better information. Not to mention the ability to flash this when there's an alarm, have these other indicator lights here that can flash or remain steady. All of that's more information visually available to the operator. Because the way this is designed, if you used a PLC to run your closed loop algorithm, had the output of that go to a traditional SCR control, but then you also needed an actual speed display. That's 3 components you need in a panel. All of that functionality is integrated into one package in a digital control. We can actually have alarm outputs, like I mentioned, one or more alarm outputs based on health of the control itself or what's going on in the application, in the operation itself. Is my actual motor speed outside of some sort of limit? Has my motor been running to where like I mentioned before, if it's running full speed, I can alarm on loss of encoder input. So there's many things that we can do to avoid waste in the plant. If you think about it, some of these installations are fairly remote, even within the building, and a lot of product could be wasted. Whereas if we had an alarm output, we would know right away there's a problem and we need to shut things down. There are configurable inputs, meaning that we can have limit switches, contacts from PLCs. With serial communication, it can be direct data sharing back and forth. But basically, we can tell the drive to start at a specific speed. There's many different inputs that we've got available to it. I did mention serial interface before. We also have where it's desired or preferred. We can also use a 4 to 20 milliamp input rather than manually adjusting the desired speed or time or rate. On the front of the control, we actually can follow a traditional 4 to 20 milliamp signal, and it's an isolated input, as we discussed before. There's even something called a maintenance timer. Many times plants will want to provide some preventive maintenance or schedule preventive maintenance. We can actually have a real-time timer running in the control. How many hours has there been voltage going out to this motor, which is a indication of how much time that motor's actually been running, and we can set an alarm and have maintenance be performed. So let's talk about the encoder. There's some considerations for that that we need to be aware of when using a digital control. One is you need to make sure that the voltage spec of the encoder and the controller are compatible. You don't want to use a 30 volt output encoder on a maximum 24 volt input control. That's basics. Look at the voltage specs on both the control and the encoder to make sure they're compatible. Then there's the interface. Encoders can be configured and purchased in a variety of different outputs. Probably one of the most common is NPN, Open Collector Syncing Source, which is a lot of words, but there are other types, though. There are PNP outputs. There are push-pull outputs. So the important part is on your encoder, whatever this output interface or spec is, you need to make sure it's compatible with the control that you're using. And then the last thing is, since digital controls are using a pulse feedback, there are some considerations with that. The actual pulses going to the control is a product of two things. One is the pulse per revolution output of the sensor itself, but then also where is that sensor mounted, or what target is it looking at? If it's a proc sensor, it could be looking at the teeth on a gear. If it's a true encoder, it could be mounted on the motor shaft itself. But the pulse per revolution output, or the PPR output of the encoder, it's the range of that needs to be within the range of the control. So there's going to be a minimum and a maximum, and you need to make basically what you want to do is have the highest pulse per revolution output possible encoder you can to have the control operate well at the lowest speed needed, but then also make sure and look at the maximum speed needed on the motor to make sure the product of PPR and motor speed do not exceed the maximum spec of the control. Okay, there are also devices. They're a derivative of a digital control called more of an accessory, a digital control accessory. So there are devices that basically are digital closed-loop speed pods. So there is no drive itself or control in that. It is a control of sorts, but there's no motor control output directly going to the motor. It requires some other type of drive to work with this. So this is an accessory to the motor control. So this is a closed loop. Notice the encoder here. This is a closed loop digital speed pot. Has all the features of a digital motor control. It is, however, it's not limited to by the control or the SCR current and voltage ratings. So in other words, we can use this accessory with any brand, any size, any model, any type of speed control, AC or DC, that will accept a 3-wire speed pod input. So here's an application. This is where a lot of digital pots, especially closed-loop digital pots, are used. Typically used to synchronize 2 or more motors. So if you look at the setup, this is from a real application. There were 5 5-horse variable frequency drives, each controlling their own induction motor. There was an encoder installed on each one of these motors, and on the first, or the leader, or the master motor, there was a digital closed loop pot added, and so in this part of the loop, we are controlling the master speed. But all the other motors needed to run at some proportion of whatever the master is. So we also take the master encoder signal and we feed that into each follower accessory. And so we're looking for these. We're actually looking at 2 speeds. We're looking at the leader or master speed, and we're looking for our own motor or the motor in its own loop that's being controlled. Compare those two and run at whatever the percent setting is for this relationship. So this diagram from an actual installation replaced a $20,000 PLC system with a $3,000 solution. Obviously, the customer was very happy. So let's talk about programming. Programming is very simple with a basic for all of these devices. So this is a control. This is an actual motor control. These are all control accessories, but the programming at least for this brand of product, is exactly the same. You enter the program mode, go to an item, navigate the item list, change a value, exit program mode. Most of the applications that use these products really only need to change less than half a dozen values. Now, in the case of serial interface, that means that the control or the control accessory can be connected to a computer, whether it's a laptop or an actual PC in a control room or in an engineer's office. All the configuration and control can be done remotely through a remote computer. Okay, so we're almost done. Let's talk about how to choose the right control for your application. So really, we've already talked about all the selection criteria. We need to think about supply voltage. What's available? If I'm designing a piece of equipment, I'm an OEM. Where is this machine going to be used? Is it going to be used in the home where only 115 volts is available? It's going to be also sent to Europe where it'll have 220 volt. So you got to look at what's the supply voltage going to be. Then you need to look at the motor voltage. Have I picked a motor that's going to do the work I need it to do in terms of its torque, but also is it a motor voltage spec that will line up with a readily available speed control in our case? What's that motor going to be doing? What work is the motor going to be doing? Does it need to reverse? Does it need to move a high inertia load? Is it lifting a load? All of those things need to be considered. And we just talked about that. Where is the control going to be installed? Is it going to be in a panel? Is it going to be mounted out by itself? Is it going to be outdoors? Does it need to be washed down? All of those will impact your control selection. What kind of environment is it going to be placed in? Will it be dusty, dirty, oily, corrosive? All of those need to check the compatibility of the control to those kind of environments. Do I need to ever change the direction of the motor, forward, reverse? How often? Under what conditions? Those things all need to be factored in. Am I going to need to, how am I going to start and stop the motor through the control? Am I going to walk over to the front of the control and flip a switch? Or do I need to do it coordinated with some other function? Do I need to send a remote signal to the control? Can it do that? And then finally, is there going to be any advantage or need for remote connectivity? And again, specifically talking about serial networks, Bluetooth, Ethernet, all of those kind of things. So if you are able to discuss those items or determine those items for your application, then you'll pretty much be able to narrow down your choices in terms of a control. If there are any questions about what we've discussed today or anything about an application down the road, we would encourage you to contact us here at Dart Controls. There's some email addresses there. Obviously, the phone number is 317-873-5211, and our address and our website. Please feel free to contact us. We would love to discuss your application. Thank you for your time today.